Hess's law is the next way we're going to try to find the enthalpy of a reaction. So it's going to be a lot different from the calorimetry questions that we did previously. Depending on the type of math you like to do, you might find it a lot simpler, just based on the fact that there's definitely fewer calculations, but Hess's law is definitely more of kind of like solving a puzzle and putting things together. So in this lesson, there's an appendix for Hess's law. So there's a bunch of different reactions with enthalpies for those small reactions. We'll need to use those to complete your homework for it. Otherwise, we just need to figure out kind of how to add those together and how to rework them in order to add them together in order to make up our final reaction. So Hess's law is also called the Hess's law of additivity. For that reason, we're going to add up reactions in order to make the overall reaction that we're looking for. So that's possible because Hess's law is based on the idea that the enthalpy change for a reaction is independent of the reaction route, meaning as long as we are still getting from point A to point B, our reactants are still becoming the same products, we should have the same enthalpy change for that reaction, no matter what kind of steps it had to go through along the way. So clearly this is not an actual chemical process like we'd usually see in a lab, but here's our example, and I found this graphic online, so that's why I've got kind of a, hey, please don't do this. So process number one, if we're making apple juice, maybe we just put apples under some extreme pressure and we pop out apple juice as a product. Cool, one-step process. Maybe another company makes apple juice a different way by using process number two. Perhaps it's 2 steps where we have apples and we're applying pressure again, and we end up with the products of apple concentrate and water. I'm sure you've never written a reaction where you put a minus sign, it's always pluses, right? So instead of writing water on this left side, let's bring it over to the right and say we've got products, apple concentrate and water. And then in step 2 of our reaction, we take that apple concentrate and water and we come out with apple juice in the end. So some of these things are crossed out, right? So the way you can cross something out would be if it appears on opposite sides of our arrow. So apple concentrate can be crossed out because it was a product here and then it was used up as a reactant. So we're going to cross it out. Water is the same thing but harder to see in this example just because it should be written as a product. And so it's a product, it's a reactant, we can cross it out. Those are intermediate substances. So not really a reactant, not really a product, but something that was created in the middle of that and then got reacted back off. So process 1, process 2, same starting point, same ending point, just a different route to get there. They should, following Hess's law, have the same enthalpy change. So a few different basics before we play with Hess's law ourselves. So here's one reaction. It might be on that appendix that we're given. And here's the enthalpy change for it. If I were to double this reaction, so instead of just reacting 1 carbon and 1 water, I'm reacting 2 of each and forming 2 of the products, I also have to double what my enthalpy is. So I've times it by 2. This enthalpy change is now twice as much as it was if I double my reaction. If I had to triple it, I would multiply this value by 3, quadruple it by 4. If I had to halve it, I divide it by 2, that kind of thing. So when we're playing with Hess's law, we have to usually change some stuff about the reactions that we're adding up. And whatever we do, we have to do the exact same thing to our enthalpy because this is what we're trying to find anyways, the enthalpy of the overall reaction we're trying to add to. So we might multiply some stuff. We might also have a reaction, but we want it to be in reverse. So maybe we see it on our appendix page. We have carbon plus oxygen going to carbon dioxide with an enthalpy number. But what we really need to add into our reaction is the opposite of this, carbon dioxide becoming the carbon and oxygen gas. So we can do that. We can flip things around, but then we'd also have to flip around our enthalpy. And to do that, what we need to do is change the sign that we have. So if it was an exothermic value, it's now going to become an endothermic value. The digits will all be the same, just the sign in front is going to change. So multiplying a reaction, make sure you also multiply your enthalpy. Reversing a reaction, we're going to change the sign. And maybe you'll also have something that has both things together. So you might have to reverse it and multiply it. So a couple of examples. This one's one of my favorites. So anyways, we have, using Hess's law, let's calculate the combustion of 1 mole of liquid benzene. So we only want 1 mole. So I have already balanced this in order to have 1 mole of liquid benzene. Thing is, this is totally doable, but a lot of people really hate fractions. So if you want, you can multiply this whole thing by 2 so that this fraction goes away. So instead of having just the 1 mole of liquid benzene, we now have 2, and we have double of everything else as well. The thing is, just because the question asked us for 1 mole, we're going to have to make sure when we get to the very end that we're reporting an enthalpy change for 1 mole. So there's just a step we'll have to do at the end. So I've put a box around the overall reaction that I'm going to try to add to find. So using different reactions from that appendix page, I'm going to find ones that work in order to add only to this. No extra stuff, no things missing. It has to add exactly to this. So I can't leave this program to actually show you something else, but you'll be able to find these 3 on that page. And the reasons why I picked them and how I got to them would be, I found liquid benzene as one. There's only one reaction that involves liquid benzene, so I know I need to use it. There are very few carbon dioxide ones, so I used one that had carbon dioxide and carbon, just because I knew that this one had solid carbon and it wasn't in my overall reaction. I would need another reaction that has solid carbon in order to be able to cross it out. And then if you've got a third reaction, usually it's going to be a water reaction. And there's 3 different water reactions on that page. So just be careful because we've got 3 different types of water, right? It can be gaseous, liquid, solid. So pay close attention to the fact that this is gas. So we want to make sure we also use the same state when we look to that appendix page. So these are the 3 reactions that I stole directly from that page. I haven't played around with them. I haven't multiplied or reversed them yet. That's what I'm going to do underneath here. So I'll look at the first reaction I have. I'm forming liquid benzene. I'm forming 1 mole of liquid benzene. However, in my overall reaction, I want to react 2 moles. So I want to multiply it by 2, so I have 2 moles. And I also need to flip this reaction around, right? So that liquid benzene is now a reactant instead of being a product. So I've taken the delta H that was given to me, I've times it by 2, and I've flipped the number, or the sign, sorry. So I now have negative 97.7 kilojoules. I've taken everything, I've multiplied the moles by 2 from what they were over here, and written it back out. Awesome. So that's my first reaction. I haven't been able to add anything up together. All these crossouts and stuff are still to come. My second reaction is going to help me get rid of this carbon that I don't want, and also help me get this carbon dioxide into the reaction because I do want it. It's in this box right here. So you can either look at the carbons or look at the carbon dioxides that you want and see that you want to multiply this guy by 12, right? Because we want to make sure we have 12 carbon dioxides in the reaction. We also want to make sure we can get rid of those 12 carbons. So carbon dioxide is a product here. It's a product in the reaction we're using. We don't have to flip anything around. We just have to do that multiply by 12. So everything gets multiplied by 12 in the reaction, as well as the enthalpy change. So that value is going to be multiplied by 12. We're going to have something super big that we'll have in the end. Cool. So at that point, this is when we can start crossing things out and check marking stuff. So I've got the 2 liquid benzenes that I'm going for. I'm going to check mark that. I'm happy about that. The 12 carbons, solid carbons, I can now cross those out because I have them on either side of the reaction. I know that looks like CO, but it should just be C. So those cross out. Cool. We have 6 hydrogens. We can't cross those out yet because we didn't add anything else on the opposite side. We have 12 oxygens. We're trying to get 15, so we need 3 more. I made a little note. And we have the 12 carbon dioxides we were looking for. Cool. So we need 3 more oxygens. We need 6 waters. And we need to get rid of those hydrogens still. That X doesn't exist yet. So that's where our water reaction comes up. So this one's a bit harder because obviously we've got all 3 components that we need, or we're trying to get rid of, or that we don't even have yet. So my advice would be to just look at the water and make it easier on yourself. You need 6 of these. This is balanced by 1. Instead of looking at things that have fractions, it's much easier for you to just look at water, say I need 6 of these, I'm going to put in 6. I'll check my math when I get there. Let's multiply this whole thing by 6, including my enthalpy. I don't have to flip it or anything because this gaseous water is a product, just like it is in this box. Cool. So let's multiply everything by 6, multiply the enthalpy by 6 right here, and then check things out. So yes, I got my water. Cool. I had my 12 oxygens. I said I needed 3 more. Cool. It adds up to be 15 with that 3. And finally, we're able to cross out those hydrogen gases because we have 6 hydrogen gas on either side of the reaction. So we draw a super long line and make this look like an addition equation. So anything that isn't crossed out gets written below. Didn't cross out the liquid benzenes, gets written below. We can summarize all of these oxygens together to be 15 oxygens. We have 12 carbon dioxides, and we have 6 gaseous waters. So what we write down here should exactly match what we had in the box above. So it feels like you're done because you've done all of this adding and crossing out. You've been able to make the overall reaction that you were searching for. The big idea to Hess, though, is to find the overall enthalpy change of this reaction. So the big thing we need to do now is just to add all the overall enthalpies that we just found. So adding that negative 97.7 to that negative 4738.8 and the final number, and it should pop out to being this value. Making sure that we still use kilojoules because that's what all of our values were given into us. Again, you just got a value and you feel like you're done, but remember that we multiplied by 2 at the start to get rid of that fraction. If you didn't and you went through the entire reaction with a fraction, you would be done because we were asked for 1 mole. But right now we found the enthalpy change for 2 moles of benzene. So we want to divide that by 2 in order to get to a value for just 1 mole. So that is Hess's law. Big puzzle. Hess's law part 2. We'll do it again. So I had an example already written for you, and it was balanced. If you are given a question and you don't see any coefficients, just make sure that it is balanced. Some of them you don't need to do anything to, right? But this guy, let's just make sure we've got 2 hydrogens, 1 sulfur, 4 oxygens, and then our oxygen count is off. So remember that the easiest way to do that, if your oxygens are off, we've got 4 over here, 1, 2, 3, 4, 5. The easiest way would be to throw a half right here. So now we'd have 4 oxygens on either side. Totally cool to go through Hess with that. Perhaps you hate fractions. I've already taken the fraction out. And so I multiplied everything by 2. That removed that fraction and made 2's everything else. Cool. So I've squared it off. That's my overall reaction that I'm going to try to find little reactions and add them together in order to use Hess's law and find the overall enthalpy of this guy. I'll let you look through it on your own. The reason I used these ones would be I needed something with H2SO4 and there was only one. I needed something with SO2 and there was only one. It also helped me get rid of that S8 that I didn't need. And then I needed that water equation that I said would usually pop up. And because I've got a gaseous state, I made sure I used the one that was also a gas. And then once you have what you're working with, as long as you work your enthalpy correctly and make sure whenever you multiply or flip and do something to your reaction, you do the exact same thing to the delta H, you should be good. I did again divide by 2 once I got to the end, just so that I would have a per mole instead of being for 2 moles of sulfuric acid.